So first, I want to thank Ingrid and Bjorn for putting this paper on the program. It's very exciting to talk about fintech with this very relevant audience. So this paper, I think, has implications for example, the design of investment crowdfunding, and potentially also have implications on some other fintech topics. But for the sake of time, in today's talk, mostly I'm just going to be focusing on very simple story. And I want to just carry the message through within that very simple story. And once you can understand the intuition of that story, I hope that the implications, the generalizations, the applications will become very clear by the end. So as you can see from the title, is this one working? As you can see from the title, this paper is about wisdom of the crowd. So in case this term wisdom of crowd is new to you, effectively it just means that wisdom of crowd just means the collective opinion of a large group of individuals. And the reason why we are interested in understanding and analyzing wisdom of crowd is because there are a lot of empirical evidence showing that the collective opinion of a large group of individuals often dominates the opinion of any single individual or even a single expert. And the reason behind this is effectively a law of large number argument. Because if you ask a group of people about a particular variable of interest, every person will have their own opinion about or own assessment about that particular variable of interest. And their assessment will contain some idiosyncratic noise. And if we can aggregate the assessment from a large group of individuals, then by law of large numbers, the idiosyncratic noises in their own assessment will be canceled out if we optimally average these private assessments. So because of this law of large number argument, here exists the wisdom of crowd effect. So although the particular term wisdom of crowd only came into mainstream after the arise of Web 2.0, but I think the idea of wisdom of crowd actually is deeply rooted in economic thoughts. Even it goes back to, for example, when Hayek talks about the decentralized possession of information in his famous 1945 American Economic Review paper, or if you look at, for example, his book on the road to serfdom when he was talking about talking about the capitalism, why market economy is great in terms of aggregating information. And also, if you look into those classic noisy rational expectation literature, for example, Hell of 1980 or Diamond and Barakia 1981, they don't use the word wisdom of crowd, but the setting, the assumptions that I have kind of embeds this particular idea. And also nowadays, there are actually a lot of more empirical evidence, also some theoretical analysis into wisdom of crowd. I list some of the literatures here. So what this paper is trying to do is this paper is going to take the assumption that the wisdom of crowd exists and going to ask the question, how can we harness the power of wisdom of crowd? And the particular angle that we are going to look at is to look at how can we use contract designs. In particular here, I have some smart, quote-unquote, contract designs to harness the power of wisdom of crowd. And for the fintech audience, you probably can see an intended pun over here. So, as I said, throughout today's talk, I'm only going to be focusing on the very simple story. So the story just basically summarized this in this one slide. I'm thinking about a risky investment opportunity, and I'm also going to be focusing on the smallest possible crowd as possible. So the smallest possible crowd is only going to be containing 2 investors, and I named them Alice and Bob. So Alice and Bob are thinking of putting money into a scalable, risky investment opportunity. And the choices that they have to make is just basically how much money to commit to this investment opportunity. And when Alice and Bob are deciding how much money to put into the project, their decision is basically based on a return-risk trade-off. And I assume that Alice and Bob are deep-pocketed, and also, just for exposition ease, I assume that they are identical risk-averse, but this is not really necessary for understanding the end result. So the wisdom of crowd assumption is embedded in the fact that when Alice and Bob are choosing how much money to put into this project, they each have a private information about what the return of the project is. So because the private information comes from independent information sources, so if you are, for example, if you are Alice, when you are making your investment choices, ideally, you would like to know what Bob thinks about the return of the project. And you probably want to average your private information somehow with Bob's private information so that you can make more informed investment decisions. But in most cases, in this case, for example, in two investors' case, it's easy for Alice and Bob to sit and talk to each other. But this two investor case is just trying to capture the more general case of, like, for example, 1,000 investors trying each have private information about the project. So I take the assumption that what if Alice and Bob cannot actually talk to each other and exchange their information? Are there other ways to circumvent this? Actually, what we are going to ask is, can we actually design a compensation contract to Alice and Bob so that they don't have to talk to each other, but we can actually replicate the effect of costless direct communication? So another way to put into this question would be, when Alice and Bob have put money into this project, and in the next period when the project return is realized, how should the payoff be divided between Alice and Bob? So this basically is the simple story and the simple question that I'm going to spend most of the time talking about today. So if you think about two investors putting money into the project and ask about how the payoff should be divided between them, the most natural response you can think about is so-called what I call common stock. Basically, just divide the payoff in proportion to their initial investment. Okay. The question is, under the assumption of wisdom of crowd, is this really optimal? The problem with those typical common stock approach is that it actually creates a winner's curse problem. Because when investors, when Alice and Bob have private information about the return of the project, effectively when they're making their investment decisions, they're kind of like engaging in a divisible common auction. And when we talk about a common value auction, the problem comes out of this is going to be the winner's curse. Because if Alice, for example, got a signal telling her that the project is very valuable, and she may wonder, there could be two possibilities. Either the project is really good and it's worthwhile to put a lot of money into it, or it could be just that Alice's private signal contains some very high idiosyncratic noise. So when that's the case, she puts in a lot of money into this project, but it turns out that it was just basically a mistake, so that she will be overly exposed to her mistake. And with that taken into account, Alice would rationally shred the investment amount that she's willing to put into the project. And that is going to make her not utilizing her information enough, in making the aggregate investment choices from Alice and Bob not optimal. So what I'm going to propose, in the simple case in which Alice and Bob have identical risk averse, and the optimal thing for them to do, surprise, surprise, is for Alice and Bob to equally divide their payoff, regardless how much money they each individually put into this project. So just to illustrate what do I mean by equally divide the payoff. So I'm going to give you a simple numerical example. So the first panel here, I'm showing just a case of common stock, and then I'm going to compare with the second case of 50-50 profit sharing. So suppose that Alice finds it's optimal to invest $200 into the project, and Bob finds it's optimal to invest $100. So the total investment is going to be $300. And also let's assume that, just hypothetically, for example, the realized return is 10%. So under the common stock approach, Alice will be entitled to 2/3 of the final payoff. Because the final payoff is going to be 300 times 1 plus 10%, which is 330. So Alice will be entitled to 220, and Bob will get back 110. This is the typical familiar common stock approach. Now let's assume that Alice and Bob agree to have 50-50 profit sharing. So what do I mean a profit sharing? It means that when the project payoff is realized, Alice and Bob will first get back their initial investment, and whatever remains is going to be equally divided. So in this case, if Alice and Bob still invest 200 and 100 into this project, the net payoff is going to be 300 times 10%, which is 30. So Alice will get back 200, that's her initial investment, plus 1/2 of the incremental part, so that which is 15. So Alice gets back 215, and Bob gets back 115. So this is what do I mean by a 50-50 profit sharing. So if you compare these two cases, you may immediately ask, if I am Alice,
why would I want to ever go 50-50 with Bob? Because under common stock, I can get back 220, and under profit sharing, I can only get back 215. If I'm Alice, why would I ever want to do that? So if you pay enough attention, you can actually see that. When I compare these two cases, I assume that the optimal investment for Alice and Bob does not change. In reality, what happens is that when the compensation contract for Alice and Bob is different, the optimal investment amount for them will also be different. And on average, because a profit-sharing contract essentially provides better risk sharing for the mistakes contained in the idiosyncratic noise of each investor's private signal, on average, under profit sharing, Alice and Bob will be willing to put more money into this project. So Alice, even if she agrees to go 50-50 with Bob, on average, she will be entitled to a smaller piece of a larger pie, which tend to actually be larger than the larger piece of a smaller pie that a common stock approach will give. Just to illustrate this point, let's just look at the pie chart. On the left-hand side is the common stock contract, and on the right is the 50-50 profit-sharing contract. Alice and Bob, for example, both invest $200. And suppose the project goes up by 10% in both cases, so the pie just becomes larger. And under common stock, the division of the payoff is proportional to initial investment, while under the profit-sharing contract, the incremental part is equally divided. So this still, once again, is assuming that the optimal investment amount doesn't change under these two contracting solutions, arrangement. What actually happens is that under profit sharing, both Alice and Bob, on average, would be willing to put in more money into this project and making the pie a little bit larger. So in this case, Bob is going to be entitled to a larger piece of a larger pie. So Bob is definitely happy. But Alice is going to be entitled to a smaller piece of larger pie. And I can show that actually this smaller piece of larger pie is actually larger. So for both Alice and Bob, under a 50-50 profit sharing contract, they will fare better than under the typical common stock. So actually, the common stock you can think about is like a special case of profit sharing when wisdom crowd does not exist. Whenever wisdom crowd exists, I'll show you that actually having a profit sharing contract is going to be better. So hopefully this kind of gives you the intuition of why having some profit sharing contract is better than common equity, common stock. Now what I'm going to show you is just basic use like formal mathematical models to rigorously prove that actually you can do no better than having a 50-50 profit sharing contract under this very special case. So this slide basically just formalizes the model that we have seen. As I said, Alice and Bob, two deep-pocketed investors, and their preference is captured by a constant absolute risk aversion utility function. So that takes this form. So rho basically captures their risk aversion. As I said, I assume Alice and Bob are equally risk averse, so their risk aversion are all captured by the parameter rho. And in more general cases, we can generalize the model into cases in which Alice and Bob do not necessarily have the same risk aversion. The risky investment project, the return is denoted by a random variable r tilde, and each investor's private signal is just going to be the realization of r tilde, which I denote as r, plus some idiosyncratic noise, which I denote as epsilon. So the I are just going to be index that captures either it's Alice or it's Bob. And S represents for signal, so SI is going to be investor I's private signal. And for the sake of this talk, I assume that the idiosyncratic noise follows a mean zero normal distribution. This can be relaxed further, but I'm not going to bother into that in this talk. All right. So now what I'm going to do, because I want to show you that you cannot do better than 50-50 profit sharing contract. So I'm going to consider the investment strategy functions and also the payoffs that Alice and Bob can get under three cases. The first case would be the typical common stock case. And the second case would be the case that Alice and Bob still have common stock, but they are allowed to talk to each other before making their investment decisions. And apparently, this is going to be better than the first case because both investors will be able to make more informed decisions. And the third case, what I'm going to consider is to look at investment strategy functions and the payoff under a profit-sharing contract. And the goal is to show that the payoff that Alice and Bob can get under the third case will be exactly the same to the payoff that they can get in the second case, which they have which they have common stock, but they actually can talk to each other. Right. So first case, simple common stock. So this, let's take a look at investor I. Let's assume that I is Alice. So let's look at from Alice's perspective. Alice would like to choose her investment amount to maximize her expected utility. And the expectation is going to be conditional on the private information that she has. Right? So she chooses X to maximize her expected utility, which is plugging her utility function and taking the expectation conditional on her private signal, which is SI or SA or SAlice over here. And in the paper, actually, I can show that basically I can solve for this problem without specifying any distributional assumptions on the return R tilde. But just for the sake of this talk, for simplicity, I assume that R also follows a normal distribution. Then that can give us a closed form expression of how much Alice is willing to put into this project. And if we do the math, and we can show that actually the optimal investment strategy for Alice is going to take the form of the last line over here. Essentially, the investment strategy for Alice is going to be an affine function of her prior of the return of the project, which is R bar, and her private signal, which is SI. And the weights are just going to be the relative precision of these two signals. And of course, the investment strategy is going to be normalized by the risk aversion parameter rho. Right, so this is the investment strategy under the common stock. The second case, which I will call a full information benchmark, is just that Alice and Bob, they still have a common stock arrangement between them, but they can talk to each other before making investment decisions. So from Alice's perspective, once again, she would like to maximize her expected utility, but the expectation now is just going to be conditional on two signals, because she now talks to Bob, so she knows not only her signal, but also Bob's signal. And very similar math, we can find that the optimal investment strategy for Alice is going to be also a weighted sum of the prior of the return, which is R bar, and the two private signals, SA and SB. And the weights are once again going to be the precision of the prior and the two signals. And of course, once again, her investment strategy function is going to be normalized by her risk aversion parameter. So we'd just like to stare at this last line for a little bit longer, because this is going to be something that I would like to compare with once I have introduced the investment strategies under the third case, which is the profit sharing case. Okay. So this is the full information benchmark. All right, so the third case, which I think is the most interesting case, would be the case in which Alice and Bob agree to share profits equally. Under this case, once again, let's think about Alice's problem. Alice would like to choose an investment amount, X, to maximize her expected utility. Now, Alice and Bob cannot talk to each other. So when Alice is trying to maximize her expected utility, the expectation is once again only conditional on her private signal. But what is different now here is because Alice and Bob, they agree to share profits equally. So when Alice tries to maximize her expected utility, she knows that her payoff will be partially dependent on what Bob invests, which is going to be dependent on Bob's private signal, which is unknown to Alice. So Alice basically has to form a belief of how Bob is going to invest based on her private signal. So this basically, the solution just constitutes a Nash equilibrium. The formal definition of a Nash equilibrium in this setting would just be two investment strategy functions for Alice and Bob, XA and XB, so that for each investor, for example, for investor A, for Alice, given the correct belief of Bob's investment strategy functions, the strategy functions for investor A is going to be optimal for Alice. Right? And in the equilibrium, Alice's belief of what Bob is going to invest is going to be coinciding with what Bob is actually going to do. So in this case, when I make a lot of simplifications for, like, for example, the distribution of the return, and then I can basically just use a guess and verify approach to solve for the Nash equilibrium. In the paper, I can actually show the uniqueness and the existence of a Nash equilibrium. But for the talk, I just basically just use a guess and verify approach. So inspired by the form of the investment strategy functions in the previous two cases, because we have shown in the previous two cases the investment strategy is an affine function of the private signals. So here I basically also just form a conjecture that the investment strategy for Alice and for Bob is also going to be an affine function of their private signals, and then use that conjecture to plug into the definition of the Nash equilibrium, and then use a method of undetermined coefficients to solve for the optimal investment strategy. And just kind of a technical technical note here is that on the right-hand side, basically what we are going to do is to solve for the expectation of a chi-square distributed variable, which has closed form expressions. So once we have went through all the math, what we can show here is that the optimal investment strategy for Alice and Bob is once again, by definition, right, because we take the conjecture that it's going to be an affine function of their private signals, so we have an affine function of their private signals. And take very similar form with the case of common stock, except that now Alice and Bob, they're in their investment strategy functions, there's going to be an additional 2 in front of their private signals. So this kind of captures the idea that we mentioned earlier, is that on average, Alice Bob will be willing to put more money into the project because they become more responsive to their private signals. So under this case, if Alice and Bob, given their optimal investment strategy functions, then we can solve for what the payoff that Alice and Bob can get. So from Alice's perspective, it's just going to be the return of the project multiplied by 1/2 of the total investment because they have profit sharing, equal profit sharing. So the red line over here is going to give the payoff that Alice can get under profit sharing. Then if we remember, and from the second case, from the full information benchmark, what the optimal investment amount for Alice and Bob is, then we can also find the payoff for Alice and Bob under the full information benchmark. And what we can notice that these two payoffs are exactly the same. So this kind of gives the main result from this story is that for any realizations of the project's return and the private signals, as long as Alice and Bob agree to have an equal profit sharing contract, they can replicate the effect of direct communication without actually communicating with each other. So it is in this sense is that profit sharing essentially provides a contracting solution to help Alice and Bob to harness their collective wisdom. I'm just going to skip this slide. So I have gone through this very simple example with 2 investors with identical risk aversion. If there are a large number of investors, an arbitrary number of n investors, each have different risk aversion parameters, the similar result is going to carry through. As long as the risk sharing, as long as they agree to share profits in proportion to their risk tolerance, then we can achieve the same result, meaning that namely that Alice and Bob do not have to talk to each other. But under this sharing contract, they will achieve a payoff that looks exactly the same as if they have common stock and then can freely communicate to each other. So profit sharing, once again, gives a contracting solution to harness wisdom of the crowd. So we have gone through this kind of example. Then the question is like, why are we interested? Why shall we study this example? So one application for this result is going to be the so-called investment crowdfunding. So investment crowdfunding, at least in the US, is actually a new thing. I think in the Europe, probably people are more familiar with that. Basically, just like a large group of individuals presumably have some wisdom of crowd, and they are deciding putting money into an investment opportunity. So at least in the US, currently there are a lot of different contracts offered to investors by those crowdfunding platforms. But we don't really have a good theoretical result telling us what should be the optimal contract that is offered to these investors. So I think one implication from the result that we have is that if the goal of a crowdfunding platform or the entrepreneur raising finance is to harness the collective wisdom of the investment community, then probably they want to incorporate some profit-sharing elements into the contract that they offer to investors. And the second case is that because so far when people talk about wisdom of crowd, it's usually just talking about like from the entrepreneur's perspective, by averaging the investment amount from investors, the entrepreneurs can learn from the crowd wisdom of investors. But actually, from a profit-sharing contract, what we are making is to make the investors themselves benefit from the crowd wisdom that they create themselves. So this kind of gives a new way to look at wisdom of crowd. So since I'm running short of the time, I'm going to skip a set of robustness results, basically arbitrary returns, distributions of return, potentially costly information acquisition, and if projects have the economy to scale, all the main results are going to hold. So last word is, I think just like so far I'm kind of applying these results to, for example, investment crowdfunding. I'm thinking about maybe it has the potential to also provide some guidance on the organization of, for example, DAOs, or the design of ICOs. And that's basically all I want to offer, and I'm looking forward to the discussion and your comments. Thanks.